Good day, class. In the previous video, we learned of a differentiation technique for expressions that is composed of products, quotients, and powers. In the next two videos, we will be dealing with the derivatives of classes of functions that we have not discussed before. In particular, in this video, we will learn to differentiate the class of the form f to the g, or of a function raised to another function. Now, without further ado, let us begin. Now, we have already discussed a lot of types of derivatives, especially those that deal with bases and exponents. For example, if I have the expression x to the n, the derivative of this function will just be nx to the n minus 1, while the derivative of a to the x will be a to the x ln a. Now, both of these quantities have bases and exponents. So the good question is, how do you differentiate x to the x? Or we have an expression of x that in the base, and you also have an expression of x in the exponent. The better question now is, how do you know when to apply the power rule or the derivative of x to the n? And how do you know that you're going to use the exponential rule, the one that we use to differentiate a to the x? A classic mistake is to ask where the x is, or that is, I will use the power rule if the x is in the base, and I will use the exponential rule if the x is in the exponent. Unfortunately, that is not precise. The correct way to know which rule to apply actually comes from what we call the constant part. And that is, if I have an expression x to the n, I can only use the power rule to get the derivative nx to the n minus 1 if the exponent is constant. So it is very important that you know that n here is a constant value. For example, a real number, possibly a rational number, or can be an irrational number, but it's definitely a constant with respect to the variable x. And you will know that I will use the exponential rule, or the derivative of a to the x, if the constant part will be the base. In this case, the base here should be a positive number, not equal to 1. So as long as the constant part is as long as the exponent is constant, I can use the power rule, and as long as the base is constant, I can use the exponential rule. Thus goes to show that for the expression x to the x, since none of the base and exponent are constants, then I cannot use any of these two rows. And one of the common mistakes for this topic is to use either the exponential rule or power rule to get the derivative of x to the x. So how do we now deal with this? Since I cannot use any of these two rules, I need to be creative. There are two possible solutions. Let's demonstrate that through the following example. I want to find the derivative dy over dx if y is equal to x to the x. You will notice that I have this assumption that x is a positive number, because if x is non-positive, we'll actually have a problem in defining this function here. Most of the time, the restriction x greater than 0 is for formality, and if you want to nitpick on the smaller details of the quantity. But the technique itself on finding the derivative will be exactly the same. The first technique, or the first option, will be to use the technique that we have learned in the previous lecture, and that is the logarithmic differentiation. If you refer to the left side of your screen, we have the steps already put there on how to apply logarithmic differentiation. The good part of this topic is that though we have 3 steps in the normal logarithmic differentiation, whenever you deal with a function to the function, because of the underlying assumption that the base should be positive, you can actually omit the first step. And that is, you start with taking the natural logarithm of both sides, ln y equal to ln x to the x. Of course, we do not stop here, as what we want is to apply the properties. In this case, the property that I will be using is the exponentiation property of logarithms, which gives us ln y equal to ln x ln x. We can now implicitly differentiate both sides, and I'll have 1 over y dy over dx, and the right hand side will become a product. And that means I'll use product rule. It's the derivative of the first, which is 1 times the second, plus the first times the derivative of the second. Of course, you can simplify this and multiplying both sides by y, I'll have y times ln x plus 1. X here is a positive number, and thus I can cancel it, giving me 1. Of course, if you rewrite y as x to the x, I will obtain the derivative, which is x to the x ln x plus 1. Essentially, because of the fact that we have an expression of x in the base and the exponent, we cannot use power rule and exponential rule. So what we will be doing is use logarithmic differentiation to bring down the exponent and to treat this quantity x ln x as a product, applying log diff, giving us the derivative x to the x ln x plus 1. Of course, if you don't want to use this first option, there is an alternative option. And that alternative option is to write the quantity f to the g of x as e to the g ln f. We have discussed this before when we were studying exponential functions, and this is a transformation that essentially forces your quantity to have a constant base. Notice here that though the exponent of our new expression will be quite complicated, g to the x ln f of x, but at least one of the base or the exponent will become constant. In this case, the base is a constant. So for example, I can express x to the x as e to the x ln x. Now if you have a difficulty memorizing what goes to g and what goes to f, always remember, just like in logarithmic differentiation, it will just become exponent ln of the base. You never get the ln of the exponent. You see this type of logic, especially when you deal with derivatives of exponential expressions. It is a to the x ln of the base. Or when you deal with derivatives of logarithmic functions, 1 over x ln of the base. So in this case, it is always e to the exponent ln of the base. Good thing x is x and x, x is both the exponent and the base, so we have no problem. We have y equal e to the x ln x. We just proceed with the derivative, so I have still dy over dx times a equal to the derivative of the exponential. In this case, you rewrite it e to the x ln x, and then you multiply this with the derivative of your exponent. So in this case, the derivative of the exponent is a product, giving me again 1, which is the derivative of the first times the second, plus the first times the derivative of the second. And if you simplify and rewrite it again, e to the x ln x will just be x to the x, and cancelling x, I'll have ln x plus 1, yielding you the same answer. So this type of example gives us two solutions, or two possible ways to get the derivative of a function to the function, namely either use log diff or to write the function to the function f to the g as e to the exponent ln of the base. Now a good question will be the following: which is the better technique? Now, just like in most questions like this in mathematics, the answer will be nothing. It's actually a case-to-case basis. For example, when you deal with logarithmic differentiation, remember an underlying assumption will be that you have most of the things that you deal with are products, quotients, and powers. And that's true. You should use the logarithmic differentiation when you have mostly products, quotients, and powers. And if you deal with lots of sums and differences, the better solution will be to express f to the g as e to the g ln f. Let me give you an example. For this quantity, y equal to the fourth root of x plus 1 sine squared x over ln x to the fifth x plus 1 to the tangent x. It may not look like so, but one part of this quantity will actually have a function to the function, and that's the x squared plus 1 to the tangent x in the denominator. However, since most of the parts here are governed by products, quotients, and powers, then I will use log diff to get the derivative for this type of problem. However, if I have, for example, this quantity e to the y plus x to the e plus x to the y plus e to the e equal to 0, it will be very hard to use logarithmic differentiation to get dy over dx. Rather, one good approach here is to just express the function to the function part as e to the g ln f. Notice here that e to the y will have a constant base. So that means I can use the exponential rule. X to the e will have a constant exponent. So that means I can use power rule. X to the y is the function to the function. So I will express that as e to the exponent, which is in this case y, ln of the base, which is x, e to the y, ln x. Well, the last will have a constant base and constant exponent. You have three ways to do that. I can use product rule here. I can use power rule. I can also use exponential rule, or I can just use the concept that e to the e is a constant and thus the derivative will be 0. So that means it depends on how it is formed or how it is expressed, whether you will use the log diff or the e to the g ln f manipulation. But if it can be either, then you actually have your choice. For example, if I have y equal to sine to the x cosine x, a very simple quantity where we assume sine x, the base, to be positive, I can use any of the two. In this case, I'll use logarithmic differentiation. I will skip the absolute value part, ln both sides, and then I'll bring down the cosine, giving me cosine x ln sine x. Of course, you differentiate this. Implicitly, 1 over y dy over dx will be the derivative of the left-hand side. For the right-hand side, you will again have a product. It is very common that when you have a function to the function, the g ln f will always be a product, if not a quotient. And that means when you deal with these things, you expect somewhat that you will be using a product rule or a quotient rule. Most of the time, it's a product rule. So the derivative will be the derivative of the first, which is a negative sine x, times the second, ln a sine x, plus the first, cosine x, times the derivative of ln sine x, which is just 1 over sine x, times the derivative of sine, which is cosine x. Multiplying both sides by y and expressing y as sine x to the cosine x, I will obtain the following derivative. You see here that the derivative of a function to the function is not entirely hard. The thing to always remember is that you cannot use the power rule or the exponential rule in getting the derivative of classes of functions like this. The moment you actually do so means that you're not using the power rule or the exponential rule properly. So take note of that. I hope you learned well in this video. Stay safe and thank you for watching.